We're gonna be looking at artificial intelligence or AI. Um, oops. Or more specifically, reinforcement learning. So the topic is kind of advanced to some like degree, but I'm sure everyone's like kind of heard of what AI is and kind of has an idea of what it's capable of doing or like what it does. It's kind of like a buzzword these days. Essentially, artificial intelligence is split into like three different subfields or subtopics, or there's three different main like algorithms. There's supervised learning, unsupervised learning, and then reinforcement learning. So we're gonna start with reinforcement learning because it's kind of easier to grasp and it'll make a lot more sense in the future. But like the goal of today and next time and in the future is not to like teach everything because that's kind of hard, also impossible with the time we have, but just kind of go over some of the basics and some concepts here and there. So hopefully in the future, if you do end up like taking like an artificial intelligence class or something, or going into like data science in the future, maybe you major in data science or something, um, some of this stuff will come back to you. But essentially, here are some terms. And then we have this little dinosaur here because in the end, if we have time, we'll look at like a little Chrome Dino uh, AI. But yeah, so first the agent and environment. So these are just like vocab stuff that you're gonna be hearing a lot. The first one is agent. That's like what is actually moving your object, whatever you're trying to control. So if your goal is to create some sort of artificial intelligence who is able or that is able to like beat the Chrome Dino game. When I say Chrome Dino game, I mean like the game that you have on Chrome when there's no internet and like you hit spacebar. I'm sure you have all played it before, so the agent is like the main thing that you're trying to control. So in our case, it would be the dinosaur. And when we say agent, we're basically referring to the AI itself. Then the agent has a few actuators, which are essentially actions. So in our case, there's three actions. Your dino can either run forward, right, keep on moving. It could jump, like if you hit the spacebar or up arrow, that'd be like jumping. Then it can also duck. You can hit the down arrow to duck under like the occasional birds. Then there's the environment, and that's like the game itself. So in our case, it would be that little picture frame up there with all of the pixels around it. That's like our game environment. And often when we're like dealing with AI, you hear a lot of games and examples because it's easiest to explain within like an actual game because there are rewards. But we'll get to that later. And then there's also sensors. That's like the last thing from the environment. Um, those are essentially variables that your machine or your computer program takes in. So, for example, within our scenario here with our dinosaur who's able to run, jump, and duck inside that little game environment, some sensors that we might want to take in are like the distance from our agent to the cactus or from the obstacle, and the height and width of the obstacle, and then the height of the bird, the speed of the game itself. And there's also the last one, which is bias. And we'll talk about bias a bit later, but that one's probably the most important. Bias will be a sensor or it will be a variable, no matter what the environment is. The rest of these will change with the different games. So, like if you're playing Pac-Man, for example, you probably wouldn't need to have like the speed or the bird height because there are no birds. You probably have like the speed of the ghosts or the distance to the wall and stuff like that instead. But the bias will still stay there. And so we'll get to that later. And then the learning loop. This is a learning loop, or it's also referred to as the feedback loop. I think so. It's essentially where all of the actual like training or learning happens. So if you remember back in our machine learning models, we had the training stage where we were feeding the model labeled examples and I was getting smarter and smarter. This is essentially the same thing. It's the learning loop, and during this stage, your agent actually learns how to play the game and how to become really good. The basic steps are, first you reset the environment. It's like you start the game or you restart the game, pretty basic. Then your agent picks an action. So out of the three actions we had earlier, our agent picks one, either running, jumping, or ducking. And the way it picks the action is actually based on a bit of luck and randomness, as well as what it has learned from the past. So after the agent picks the action, the game returns a reward and a game status and the next state of the environment. So let's say the agent picks an action and it jumps over the cactus. Then our game status would be that the game is still going on, and the reward we would give is like plus a couple points or something, right? We'll give it a few coins or points, right? Positive points because it survived and it did something good. And the next state of the environment would just be that next frame of the game, like a screenshot basically. But hypothetically, let's say our agent chose the action and the action it chose was to just keep on running forward and it ended up hitting the cactus and dying. Well, then first our game status would be false, right? Or end because the game is over now. So, and then our reward would be minus a couple points because that was something that we did not want the dinosaur to do. We don't want the dino to die, right? So we subtract a couple points, and then with more and more like playing with inside a learning loop, the AI begins to remember the reward with experience replay. That's basically like its memory. So like how us humans, we memorize that like if I do well on my tests, I get a reward, stuff like that, or like I get good grades. There's like a correlation there. And the goal is for the AI to understand that there's a correlation with jumping over the cactus and staying alive means I get more points. And the AI wants to get more points. So he keeps on, or the AI keeps on doing that until it ultimately becomes really good at the game. And then the agent or the AI can also go back into the batch of experiences, which is like the experience replay, the memory, to learn based off those experiences. And that's basically how the learning loop works. Most important, just understand that it's a loop. And the reason why we also call it a feedback loop is because you're essentially just learning based off your feedback, similar to how us humans used to learn when we were like babies, right? You know, how do you learn to walk, stuff like that. We also went through reinforcement learning. Um, if you end up taking like psychology, I think they teach a lot of this stuff too, except it's with humans. And so that's the learning loop. And then here's reinforcement learning or reinforced learning. It's the same thing. This is the idea of a reward system. So the agent gets plus points for doing something good. So if you achieve a high score in the game, you get a bunch of points. And if you get and it gets minus points for doing something bad, so dying or achieving a low score. We already went over that. And it also learns to correlate certain actions to points, which we also kind of went over. It's like if you give a baby a cookie for doing something good, the baby ultimately gets like, it understands that every time it does a certain action, it gets a cookie. But you also want to make sure like you set your point values and your correlations correctly. Because if you end up giving positive points or plus points or subtracting points for doing something opposite, or like doing something bad, and you give them plus points, then they'll start learning to do the wrong thing. And lastly is the bias/variance. And that's the thing I was mentioned on the first slide. It's also called an epsilon or the extrapolation versus exploration. Wait, let me check that again. Oh, it's also known as the exploration versus exploitation trade-off. It's kind of a long term. You can just call it bias. But essentially, exploration versus exploitation. So exploration is the idea of like learning new stuff, and exploitation is the idea of like kind of like cheating. Like those are the definition of the two terms. And this trade-off essentially says that the more exploration you do, the less likely you're able to exploit a certain path. So let's say our dino has learned that if it spams the jump button, it'll be able to consistently get like 200, 300 points because they're lucky, right? You spam the, if you hold down spacebar, you'll get a decent amount of like progress before you end up dying. And if the dino has a very high level of exploitation, their exploitation factor is like really high, then it will just spam the spacebar continuously because it knows every time I do this, I can get 200, 300 points. And that's a lot of points. And it's going to keep on doing that. And it'll end up racking up like a lot of points that way. Exploration, on the other hand, it tells the dino that, hey, 200, 300 points, that's not good enough. You need to try new things to ultimately get more points. So what's going to end up is the dino will get 200, 300 points. Then the next time it'll get like 0 points because it tries something brand new and ends up dying, right? Because you try something new, you're probably going to fail. But it keeps on trying all of this new stuff until it ultimately finds a better solution, like timing their jumps, that is ultimately better than the exploitation scenario where it just gets 200 points and it gets like 500 points or something. So if you were to run the two exploration like scenario dinosaur who starts off very bad, very random, and it ultimately gets very good later on, versus the exploitation dinosaur who just kind of consistently does only what it already knows, which is just spamming the spacebar and consistently gets like 200, 300 points. In the beginning, you'll notice that the exploitation dinosaur is doing better than the exploration one for obvious reasons, right? But as time goes on, and like if you simulate it like a million times, then the exploration dinosaur will end up doing much better than the exploitation dinosaur because the exploration dinosaur is actually learning and getting better. And that's basically what the bias as variance is. So you want to tweak this number to like a balanced amount where it has a balanced level of exploitation and a balanced level of exploration. So it will make sure to try new things, but also once it secures like a really high score, it will repeat those same actions to try and get that high score and replicate that high score. And so that's like kind of important within artificial intelligence and reinforcement learning, especially. Um, yeah. And then moving on, genetic algorithm. So this is actually, it's not exactly part of reinforcement learning. It's technically kind of a method to solve reinforcement learning, but that's like not important. Just don't worry about it. Just know that this is a separate thing and it's called the genetic algorithm. Um, I don't know if y'all have taken uh, biology yet, but or like natural selection. Maybe you guys have, but there was that one person, Darwin, who had like natural selection. If you know what I'm talking about, you'll know. If you don't, you'll learn it like in a couple years, I'm sure. But essentially, there's this theory that humans got better and better by natural selection. Essentially, the smartest humans survived the longest and ended up reproducing. And so every generation, us humans got smarter and smarter and will keep on getting smarter and smarter. Because the idea is like the not so smart humans ended up dying before they could reproduce. That's basically the TLDR of natural selection. And genetic algorithm is basically the exact same thing, except it's implemented within a computer. Um, so it's basically natural selection with both a population of dinosaurs. So you have like 100 dinosaurs or something, and they all run at the same time inside your environment. And the ones who survive, they reproduce. And you might be like, how do dinosaurs reproduce inside like my computer, right? They don't actually reproduce, but like what happens is after all the dinosaurs die off, let's say hypothetically the top 10%, the 10 best dinos, we take those dinos, analyze their specific features and what makes those dinosaurs unique, and then we create new dinosaurs for the next generation, which retain the same features as their parents, but they have a bit of variance. So they're a tiny bit different. And they keep on doing this until generation after generation, until you get the best features or like the best characteristics of each dino. And that's it. Um, there's a new term here. It's called a fitness value. That's essentially a characteristic to determine how, or it's a method to determine how good your solution is. Um, Let me think of a good example. It's I can't think of a really good example, but essentially it's like a way to analyze how good your dinosaur is. Yeah. And the smaller your fitness value, the better your dino. So for in our case, let's say with the dinosaur game, there's a score in the top left in the actual game, right? And the higher your score means the better your dinosaur is. And so we can take that into account. So for example, let's say we have a dinosaur who has a score of 1500 and then dies versus a dinosaur who has a score of 2000, 2000 and then dies. Obviously, the 2000 dinosaur is better. And so we'll give the 2000 dinosaur a lower fitness value than the 1500 dinosaur. And then the 2000 dinosaur will end up getting chosen first when the next generation is created to reproduce that 2000 score dinosaur's features and characteristics. That's essentially how the fitness value works. That was a very simple explanation. Let's say you had like Pac-Man again, right? That's maybe not the best example. Okay, let's just say you had Pac-Man again. Um, it's not as simple to determine your score of Pac-Man because there's like more components to the game, right? You can eat the ghost, you can like pick up cherries and stuff, you can eat a bunch of dots. The time you survive might also be a factor in Pac-Man, right? So let's say like is it Pac? Or let's say the yellow guy who's eating everything in Pac-Man, the Pac-Man, right, ends up staying alive for a very long time, but it doesn't end up like eating as many dots or gaining as many points as another version of the Pac-Man, but still it stayed alive for a very, very long time. So maybe we should give that person or that Pac-Man's fitness value a lower score in comparison to the other one. So with more complex games and scenarios, your fitness value will be much more complicated to determine and analyze. But in our scenario with just the Chrome dinosaur, it's pretty simple to just to say whoever has the highest score has a lower fitness value. And so, oh, high fitness value? Uh, Pretty sure this is a typo. Uh, Pretty sure it should be the lower the fitness value is better. But that's not important. Just know that the fitness value helps determine which dinosaur should get selected for reproduction in the genetic algorithm. And then lastly, we have neural networks. So you probably have heard of this too. It's also based off a real brain. So like if you know your science, your brain is a bunch of neurons interconnected. Like I think there's just like millions of them or something. And there's also different types of neurons that do different things to create your brain. And the idea of a neural network is they kind of simulate your brain, but with layers instead. So most notably, you always have your first layer as your input layer. And so those are your sensors from the environment, your input. So like distance from cactus, how fast the cactus is moving, that stuff gets inputted. And that's always going to be the same. Then you have your hidden layers. I'll talk about those a bit later. And then you have your output layer. Output layer is usually like your actions, your actuators. So um, you're gonna get an output layer that has run, jump, and duck, run, jump, or duck, and it'll tell you, okay, based on these inputs, your best choice of action should be to either run or jump or duck. And that's what the neural network does. There's a lot of weights and biases inside the hidden layer. Each of the hidden layer has a weight and bias that ultimately correlate to the output layer. So the idea is, let's say your input layer here, you give it like, let's say this input here is the speed of the game, and it goes to this hidden layer. And the hidden layer here has a weight. And the weight is determined by training your neural network from learning. The more you learn, the more your weights will get finalized and the more your values will get like fitted properly. And your goal is to find the perfect weights for all of your hidden layers or hidden nodes. These are each called a node or neuron, whatever, if you want to think scientifically, but these are nodes. And you want to find the proper weight, the perfect weight for each of your nodes so you get a most consistent answer for your output layer. And so, for example, like the higher your weight, the more important it is. So your weight basically is a double or a decimal from 0 to 1. And with 0 being like this is not important at all, and 1 being super, super, super important. And so maybe your input layer, you have a picture, and the input layer takes in the brightness of your dinosaur. That's pretty useless. So hopefully, after a lot of time, your hidden layer, the weight that's attached to the brightness input, is 0 because it's not important. But let's say the distance to the cactus, let's say that's a different node for your input layer. Hopefully, the nodes attached inside the hidden layer to the distance to the cactus input, they have a higher weight, maybe like 0.9, 0.8, or even 1, right? Because that's pretty important. And you can have multiple hidden layers that all lead to the output layer. And the thing about the hidden layer is there's no way to describe what each of these nodes do. Like you can't describe what this is telling you. And that's kind of how um, the like magic works behind artificial intelligence. Because the idea is the brain learn or the quote unquote brain or the neural network learns by itself to determine what should be important within the hidden layer to give you the proper output layer. Um, so yeah, that's pretty much it for the terminology. I know that was a lot of stuff. It's kind of confusing, but here, let's. Um, so I have here a Chrome dinosaur loaded up. This is an example of a genetic algorithm. So first thing you'll notice is let's talk about the variables. So 500 means that there are 500 dinosaurs right now. You can't tell that there's 500 because they're stacked on top of each other, but there are 500. How many alive? All of them are alive. But watch, now there's only 23 alive because, oh, now there's only 1.6 and there's only 1% alive. It's going too fast. Okay, so now there's only 0.6 alive. So 0.6 out of the original 500 are alive because everyone else died on like the first obstacle because this is generation number 1 when nobody knows what they're doing. So it's basically just random right now. The fitness average currently is 0, but after the next generation, you'll see the fitness average kind of like improve or like actually get to a proper number. The target score is related to the score down here, like what we're trying to aim for. We're hoping that these dinosaurs can ultimately reach 1000. Currently, they're at 193. And the speed constantly increases, and the speed is referring to the movement of the environment, like how fast the cactuses are moving, or cacti, sorry, are moving. Currently, they're moving at a speed of 5.1. I don't know what the units are, but it's 5.1. And high score is just high score. And this slider here controls how fast and how slow. So currently it's at the slowest speed, but we can make it go a bit faster. So let's make it go a bit faster for these people to, I don't just say die, but like to hit the cactus. Okay, so now this is second generation. Slow it down a bit. So you notice the second generation, the high score is updated. The fitness average is also updated. It's 106. That doesn't really tell us anything. But after the next generation, it will update again and we can see what the difference is. You'll notice that the live percentage is back at 100 because like this is our currently like our learning loop. We reset the environment and now, oh, shoot. We reset the environment and now the dinosaurs are taking in all of the sensors and determining what action to do. And so this is a neural network where it determines what action to do. So for example, we have distance to the next obstacle, height, width, bird height, speed, bias. All of the lines are important, but they're okay. The line colors, essentially, I forgot which, but one of the line colors was to determine, I think the darker the color is, the more important it is. I could be completely wrong. But the lines aren't that important. Just know that they're essentially like some of these values from here are coming to this node, which then comes to this node. And I'm pretty sure the more dark or the stronger the intensity of the line is, the higher the weight of these nodes are. But I did forget what the blue and red difference was. I think the blue lines are the brain of the last champion. So the brain of the last champion, his features, or sorry, the dinosaur's features are that set of neural network. And the red ones is just in general the average of everyone. And so let's speed it up a bit. Okay, so point two are alive. Not bad. There should be only 4 dinosaurs currently. Is it 4? 4. Wait, it's gonna reach the high score. Wait, what? That's unusual. The target score has been achieved. I think it's because I'm might have been pre-trained. Okay, 100,000. And so generation 3. So you notice the fitness average went up. So yeah, I think I'm correct. The higher the fitness value, the higher the fitness average or the fitness value, the better the dinosaurs should be. And yeah, so that's pretty much it. We're pretty much done today.